Myself Dinesh, working as Assistant Professor, Department of Physics. Dear students, in this video lecture, I am going to explain the topic Michelson's Interferometer. Dear students, in this topic, we should understand the principle of interferometer. Second one, to study the construction and working of interferometer. Third one, how the interference patterns are formed. Fourth one, to study the conditions for different fringes. Let us see one by one in brief. Michelson's interferometer. Dear students, instruments based on the principle of interference of light are known as interferometer. Here this interferometer based on the principle that a beam of light from an extended source is divided into two parts of equal intensities by partial reflection and refraction. These beams travel in two mutually perpendicular directions and come together after reflection from plane mirrors. The beams overlap on each other and produce interference fringes. Here, the interferometer was invented by the American physicist Michelson during the year 1852 and 1931. Here, it splits a light beam into two parts and then recombines the parts to form an interference pattern. The device can be used to measure wavelengths or other lengths with a great precision. Let us see the construction and working of Michelson's interferometer. See here, this is the Michelson interferometer. A single ray of light coming from the light source is split into two rays by the mirror M1, which is called beam splitter. Here the light coming from the light source, when it is incident on the mirror M, it splits into two rays, hence this is called beam splitter. The path difference between the two rays is varied with the adjustable mirrors M1. As M1 is moved towards M2, an interference pattern moves across the field of view. You can see the interference pattern using the telescope. Let us see how it is constructed. See here, it consists of glass plate P, which is half silvered on its back surface, which is inclined at an angle 45 degree to the beam of light. Another glass plate Q, which is mounted parallel to the glass plate P. Here it is shown in the diagram. It is of equal thickness and of the same material. Here these two glass plates are made of same materials. The glass plate Q is known as the compensating plate. The mirror P is called a beam splitter because it is half silvered on its backside. Here it transmits half the light incident on it and reflects the rest. The two rays travel separate paths, that is L1 and L2. Here L1 and L2. That is L1 called ray 1, L2 is called ray 2. The plane mirrors M1 and M2. Here M1 and M2 silvered on their front surfaces. They are silvered on their front surfaces and mounted vertically on two arms at equal distance from P and at right angles to each other. The planes of the mirrors can be slightly tilted with the fine screws at their backs. There is a micrometer screw is there at the back side of both the mirrors M1 and M2. The mirror M1 is fixed on a carriage and can be moved parallel to itself. With the help of a fine screw of uniform pitch. Let us see how it works. A beam of light from the monochromatic source S, after passing through the lens, is incident on the glass plate mirror P. The plate P, due to being semi-silvered, divides the beam into two parts of nearly equal intensities, namely reflected and transmitted. Reflected and transmitted beams. The reflected beam L1, which is called ray 1 in the diagram, moves towards the mirror M1, and falls normally on it, and hence it is reflected back to the plate P. After being transmitted by the plate P, enters the telescope, telescope T. The transmitted beam L2, which is called the ray 2 in the diagram, moves towards the mirror M2 and falls on it normally after passing through the plate Q. It is then reflected by the mirror M2 and retraces its path. In its return journey, it strikes the plate P and gets reflected into telescope. Since the beams entering the telescope are coherent, that is division of amplitude, and giving rise to interference pattern. Let us see here. During the journey, the reflected beam L1, the ray 1, travels through the plate P twice. Here the ray 1, that means reflected beam L1, which travels the plate P twice, while the transmitted beam L2, called ray 2, travels once. It means ray 1 travels an excess optical path of 2D into n-1. It travels excess optical path of 2D into n-1 over the beam transmitted ray 2. To compensate this, because the ray 1 travels twice but ray 2 travels once, to compensate this, the identical plate Q is introduced in the way of transmitted beam, that means ray 2. Thus the plate Q is called compensating glass or compensating plate. Let us see types of fringes. Here these are types of fringes shown here. Here it can be analyzed by using this diagram. That means figure 1. Let us see one by one. Types of fringes depends upon the inclination of M1 and M2. See here, already seen in the Michelson interferometer, the types of fringes depends upon the inclination of M1 and M2. Let M2 dash here, seen here, M2 dash be the image of M2. It is the image of M2, mirror M2, which is perpendicular to the mirror M1, already shown. Here, M2 dash be the image of M2 formed by reflection at the plate P, so that PM2 equals PM2 dash. Thus, the arrangement is equivalent to an air film enclosed between the reflecting surfaces M1 and M2. We can refer the Michelson interferometer with this diagram. The path difference between M1 and M2 is 2T cos R. 2T cos R, where T is the thickness of air film. Suppose at the center cos R is equal to 1. Then the path difference is equal to 2T. At the center of this, cos R is equal to 1. Because R is equal to 0, then cos 0 is equal to 1. Then the path difference is 2T, twice the thickness of the air film. There are two types of fringes are formed, namely circular fringes or Hedinger fringes or fringes of equal inclination. I repeat, there are two types of fringes are formed. First one, circular fringes or Hedinger fringes or fringes of equal inclination. Second one, localized fringes or fringes of equal thickness. Localized fringes or fringes of equal thickness. Let us see one by one. First one, circular fringes or Hedinger fringes. For this one, see here, this is the diagram which shows the Hedinger fringe pattern or circular fringes. If M1 and M2 are perfectly perpendicular to each other, that is already shown in the Michelson interferometer, that is M1 perfectly to M2 dash. Here in this diagram, M1 is perfectly to M2 dash. M2 dash is the image of the mirror M2. We get circular fringes or Hedinger fringes. These are called fringes of equal inclination because each fringe is due to a set of rays reflected which are all having same inclination. Let S be the extended monochromatic source of light. S1 and S2 are the virtual images of S formed in M1 and M2 dash respectively. Here for this one you referred the previous slide. Here this slide. Therefore, if T is the distance between M1 and M2 dash, then the two virtual images S1 and S2 are separated by the distance 2T. The path difference between M1 and M2 dash will be 2T cos R. In the interferometer, the ray reflected from M2 suffers reflected at the silver surface of silver plate P, and hence the additional path difference should be lambda by 2, has to be introduced between the rays. Therefore, the path difference is equal to 2t cos r plus lambda by 2. Let us see the constructive interference and destructive interference. For the constructive interference, the condition is that we know that for constructive interference, the path difference should be m lambda. Here in the LHS side, this is the true path difference. That is 2t cos r plus lambda by 2. When it is equated with the condition for path difference, that is m lambda, where m equals 0, 1, 2, 3 and so on. That means on further simplification we get 2t cos r equals 2m minus 1 into lambda by 2. For the destructive interference, the condition for path difference is 2m minus 1 into lambda by 2. Here 2m minus 1 lambda by 2 is equated with the true path difference produced by the Michelson interferometer, that is 2t cos r plus lambda by 2, where m equals 1, 2, 3 and so on. Finally we get, on further simplification, it becomes 2t cos r equals m lambda. Let us see if t equals 0. That means the thickness of the air film is 0. If m1 coincides with m2 dash, the path difference is 0 and hence the field of view appears dark. When the image of mirror m2 is coincided with the real mirror m1, then there is a thickness of the air film should be 0 and there is no path difference. Hence the field of view appears dark. If m1 is moved either side parallel to itself, widely spaced circular fringes are produced as shown here. These are the circular fringes. Widely spaced circular fringes are formed. Now the second type of fringes, that is localized fringes. For this one, you can refer this diagram here. If m1 and m2 are not perpendicular to each other, in the Michelson interferometer, if m1 and m2 are not perpendicular to each other, then we get a wedge-shaped air film between m1 and m2. The fringes are here straight fringes or fringes of equal thickness. They are called fringes of equal thickness because each fringes is due to reflection from the locus of all points on the film which having the same thickness. See here, m1 and m2 are not perpendicular to each other, then we get wedge-shaped air film between m1 and m2 dash. The fringes are here straight fringes or fringes of equal thickness. They are called fringes of equal thickness because each fringe is due to reflection from the locus of all points on the film which having the same thickness. If m1 and m2 dash are inclined, slightly curved fringes are formed. Here you can refer this one, first diagram and the last one. You can refer both the diagram here, first one and last one. If m1 and m2 are inclined like this, then you get slightly curved fringes are formed and they are curved with their convex sides towards the thin edge of the wedge. If m1 and m2 dash intersect like this, refer this diagram. If m1 and m2 dash intersect like this, the straight line fringes are produced. Here exactly straight line fringes are produced as shown here, the middle diagram, this one. we can note that these fringes are localized in the air film and are observed up to a small part difference. The change of thickness T of the air film causes the variation of the part difference. So, these fringes are called the fringes of equal thickness. Mention of fringes of equal inclination, that means Hedinger's fringes, and the thickness should be if M1 and M2 are perfectly perpendicular to each other. That is, M1 perfectly parallel to M2 dash. We get circular or Hedinger fringes. These are called fringes of equal inclination because each fringes is due to a set of rays reflected which are all having same inclination. The change of thickness T of the air film causes the variation of the part difference. So these fringes are called fringes of equal thickness. These are the points should be noted that. Thank you.